We shall see how the bending test is performed on universal testing machine UTM. So in the last lab we have seen the working of universal testing machine UTM. The tension test was performed on UTM by placing the specimen, the steel rod between the upper head and the middle head. Now to do that bending test, we are placing the specimen on the lower head, and the load application will be done by the moving the middle head. So on the middle head there is an attachment provided which we will attach over here for doing the bending test, and that is attached to provide the point load onto the beam. Now before starting the experiment, let's revise what we have learned about UTM, universal testing machine. It's having two parts, the loading part and the control part, and here you have a dial also where the load applied can be measured. So as you know, the load is applied pneumatically. So first by electrical means, the electrical up switch and down switch are there. By electrical means the middle crosshead is brought near to the specimen, the wooden beam here. It is just kept touched on the wooden beam. Then we close this valve, and by opening this valve we can apply the pneumatic load onto the wooden beam. Now the load can be measured over here, and to measure the corresponding deflection produced or deformation produced, we are making use of an instrument called the dial gauge. So dial gauge is used to measure the deflection or the deformation occurring to the wooden beam. So it is placed, the tip of the dial gauge is placed onto placed very near to this middle head, and as the middle head moves down, the dial gauge will show the reading, how much it has moved down. That means that much deformation has occurred, that much vertical displacement have occurred to the wooden beam. So we are making use of the dial gauge to measure the deformation or deflection, and the dial on the UTM will give the load applied. So once you have the load applied and the deformation produced, then from that you can calculate the bending stress developed. Now before starting the experiment, let's determine the range in which UTM have to work. So the standard value for bending stress for wooden beam is 15 Newton per millimeter square. So we, based on that, giving a factor of safety of 5, we calculate the ultimate stress or maximum stress in bending. So for that maximum stress in bending, what is to be the load applied, that you calculate. So from the bending equation you have m by I is equal to F by Y equal to E by R, or m by I is equal to F by Y. So from in that F, depending on the giving the factor of safety, I have calculated the ultimate stress in bending. So ultimate stress in bending, that is the value that I am getting, that I am substituting for F. So I can calculate the bending moment, m by I is equal to F by Y, where you know Y is the distance of the neutral layer from the distance of the extreme layer from the neutral layer, neutral axis, and that is equal to d by 2 in the case of a rectangular beam. Then moment of inertia, that is equal to BDQ by 12. Then maximum bending moment taken is the maximum bending moment, and this is a simply supported beam. Here you can see that the beam is placed supported at the two ends. So it's a simply supported beam, and a point load, you are applying a point load exactly at the center. Okay, so for a simply supported beam with a point load at the center, you can calculate the bending moment. Where will be the maximum bending moment? For a simply supported beam, you know that the bending moment at the ends will be 0, and bending moment will be maximum at the center. And what will be that bending moment? So the total load applied here, suppose the point load applied at the center is W. So since it's symmetrical loading, the two supports will generate develop a reaction. Reaction is equal to W by 2. Reaction of the two supports is equal to W by 2 each. So what will be the bending moment at the center? Bending moment at the center will be equal to the sum of the moments due to all the forces to the left of the section or right of the section. So taking some of the moments due to the forces to the left of the section, we have W by 2. There is a reaction at that end, W by 2 into that distance L by 2. So that is equal to WL by 4. So WL by 4 is the maximum bending moment occurring in this beam, and that is occurring at the center. So that maximum bending moment WL by 4, based on that you calculate what is the maximum load that can be applied at the center. So M by I is equal to F by Y, F value you calculate based on the ultimate stress in bending for wood, giving factor of safety, you calculate the ultimate stress. So Y is the distance of the extreme layer, the maximum stressed layer from the neutral layer, neutral axis. So that is equal to d by 2, depth of the beam by 2, and moment of inertia, since the beam is rectangular in cross section, that is equal to BD cube by 12. Then maximum bending moment that is at the center, that is equal to WL by 4. So the unknown is W, the load that you can calculate. So you will get a value nearly 10 kilonewton or so. So based on that you calculate, you determine the range of the load to be selected, range for the UTM. So the lowest range possible for UTM, this UTM is 0 to 40 kilonewton. So since our load is coming well below that, I am selecting that range 0 to 40 kilonewton as the range for doing this test on this UTM. Now moving ahead with the experiment. So we have seen that we have selected the range for UTM as 0 to 40 kilonewton. So the least count will be 0.1 kilonewton. So the smallest of the division will be 0.1 kilonewton. So each of the 10 reading will give 1 kilonewton. So the one largest marking will give 0.5 kilonewton. So one largest marking will be 0.5, next is 1, then 1.5, etc. Then here the dial gauge is having a least count, it is written over there, it is 0.01 millimeter. 0.01 millimeter is the least count of the dial gauge. So you note the reading on the dial gauge, then multiply the reading by 0.01, so that you will get the deflection in millimeters. Okay, now we shall move on to the bending test. So the specimen is already placed as a simply supported beam. Then the point load is applied at the center. Now you have a dial gauge for measuring the deflection. Now I am switching on the machine. Okay, I am applying the load. So when 0.5 kilonewton is applied, so the largest big division that give the 0.5 kilonewton, next is 1, 1.5, etc. So I am taking reading at each of the largest division. Smallest division is 0.1 into 5, that will be the one largest division, that is 0.5. So at each of the largest division I am taking the reading, I am taking the deflection produced. So for each 0.5 kilonewton I am noting the reading on the dial gauge. So the load will be applied. So load is applied, we are noting the reading for 0.5, 1, 1.5, 2, then 2.5, 3, it's coming 3, not the reading there on the dial gauge, then 3.5, not the reading on the dial gauge. Yes, we have noted reading up to 4 on the dial gauge, we have noted the reading. Then on further loading you can see that the beam will fail. Fracture has occurred on the beam, and the maximum load applied is shown by the red pointer. So the maximum load that was applied is shown by the red pointer. Red pointer, black pointer ഇപ്പുറത്തായിരുന്നു. മാക്സിമം എവിടെ വരുന്നു അവിടെ വന്ന് റെഡ് പോയിന്റർ നിൽക്കും. ഫ്രാക്ചർ തുടങ്ങി കഴിയുമ്പോൾ ബ്ലാക്ക് പോയിന്റർ തിരിച്ച് പുറകിലേക്ക് പോകും, ലോഡ് കുറച്ച് കുറയുന്നുണ്ട്. So now the maximum load is given by the red pointer. So here you can see that 4.3 kilonewton is the load applied, it's a maximum load.